Hello everyone, welcome to Enviro Pioneers. In this video, we are going to explore another important meteorological parameter, that is humidity. We will learn about the different ways humidity in atmosphere can be expressed and will understand the concept of absolute humidity, mixing ratio, relative humidity, saturation vapor pressure and dew point temperature. As this meteorological parameter is something which is related to water, let us have a quick revision of some of the fundamental. There are some properties which make the water unique from other substances, like water is the only liquid which is found at the Earth's surface in the large quantities. It can readily convert from one state of matter to another, and the water's solid phase, that is ice, it is less dense than the liquid water, and water has the high heat capacity, means to change its temperature it requires the considerable energy. So all these properties, they influence the earth's weather and climate and make it favorable to life. And all these unique properties are mainly because of the water's ability to form the hydrogen bond. A water molecule, it consists of one oxygen atom and two hydrogen atoms. And many water molecules, they are joined together by the hydrogen bonds which is formed between the oxygen atom of one water molecule with the hydrogen atom on another molecule. In the liquid state, water, it consists of cluster of water molecules which are joined together by the hydrogen bond, and as these clusters they move about, they continuously break up and are replaced by the new ones. So here it is written that in liquid water the hydrogen bonds, they constantly break and reform, but the solid phase of the water, it has a crystalline structure because of the stable hydrogen bonds. In ice, hydrogen bonds, it produce a rigid hexagonal structure as we can see here, and the resulting molecular configuration, it is very open. It means it contains lots of empty spaces. But in the liquid water, the molecules, they are closer together and can move past each other, so it results in more compact and the dense structure. In this image, the difference of the molecular configuration is shown for the liquid state and the solid state. In the liquid state, the molecules, they come close to one another and are attached through the hydrogen bond. While in the solid state, these molecules, they spread out and form a hexagonal crystalline structure which increases its volume because of the open structure. And as density is mass per unit volume, this increased volume makes it less dense and therefore it floats on the water. And this property of water is important for the aquatic life in the winter season, because as this ice is formed on the upper layer, it acts as the insulating layer and prevent the entire water from getting cold and maintain a uniform temperature below this ice layer, and it is suitable for the aquatic life. Water is the only substance that naturally exists on the earth as ice, liquid, and water vapor. And in all these three forms, water is composed of hydrogen and oxygen atoms only. But the primary difference among these three phases is the arrangement of these water molecules. And when the water changes its state, hydrogen bond is either formed or it is broken. And six phase changes of the water are evaporation, condensation, freezing, melting, deposition, and sublimation. In this animation, we can see the change in the molecular configuration as water is converted from liquid to the solid state. Ice, it is composed of the water molecules that have the low kinetic energies. And these molecules in the solid phase, they form a tight, orderly network, and they are not free to move relative to each other, but they vibrate within their fixed site. When ice is heated, the molecules, they oscillate more rapidly, and when the rate of molecular movement increases sufficiently, the hydrogen bond between some of the water molecules are broken, which results in melting. And in the liquid state, the water molecules, they are still tightly packed, but they move fast enough to be able to easily slide past one another. And as a result, the liquid water is fluid and it can take the shape of the container that holds it. When liquid water is heated or it gains the heat from the environment, some of the molecules they acquire enough energy to break their hydrogen bond and they escape from the water surface to become the water vapor. And in the gaseous state, the water vapor molecules they are widely spaced in comparison to the liquid water and they exhibit very energetic and the random motion. These processes are reversed when water vapor returns to the liquid state or when water freezes. So basically, when the water changes its state, hydrogen bonds are either formed or are broken. And whenever water changes state, energy is exchanged between water and its surrounding. The heat involved when the water changes state, it is measured in the units called calories. And 1 calorie is the amount of energy which is required to raise the temperature of 1 gram of water by 1 degree Celsius. For example, if 1 gram of water absorbs 10 calories of heat, the molecules they will vibrate faster and a 10 degrees Celsius temperature increase will occur. But during the phase change, the energy may be added to a substance without an accompanying rise in temperature. For example, in the glass of ice water, when the ice melts, the temperature of the mixture it still remains a constant 0 degree Celsius until all the ice has melted. So, when the added energy does not raise the temperature of ice water, where does this energy go? So in this example, the added energy it is utilized in breaking the hydrogen bond. Because the energy used to melt ice, it does not produce a temperature change. It is referred to as the latent heat. Latent means hidden, and it is something like the fingerprints hidden at the crime scene. And when the water freezes, the energy stored in the liquid water is released to its surrounding. Here we have the further explanation for the latent heat means the energy required or released during the phase change of water. As it is mentioned that melting 1 gram of ice it requires 80 calories of heat means 334 joule and this amount is referred as the latent heat of melting. While in the reverse process during freezing, when this liquid water is converted into ice, 80 calories per gram is released to the environment, and this is referred as the latent heat of fusion. So, latent heat of melting and latent heat of fusion both are having the equal values, but one is required and another is released. Now, once this water is converted into the liquid state, further addition of calories will increase its temperature. So here it is mentioned warming. Once the liquid has attained the temperature of 100 degrees Celsius, further addition of 540 calories will convert it into the water vapor. So during the evaporation also latent heat is involved and it is referred as the latent heat of vaporization and the value it varies from about 600 calories per gram of water at 0 degree Celsius to 540 calories per gram at 100 डिग्री सेल्सियस मीन्स अगर हम 0 डिग्री सेल्सियस से डायरेक्ट वाटर वेपर में कन्वर्ट कर रहे हैं सो इट विल रिक्वायर 600 कैलोरीज बट अगर हम 100 डिग्री सेल्सियस से यहाँ पे वाटर वेपर में कन्वर्शन देख रहे हैं सो इट विल रिक्वायर 540 कैलोरीज. So, during evaporation, the energy absorbed by the water molecule is used to give them the motion which is needed to escape the surface of the liquid and to become a gas. And as this faster moving molecules they escape the surface, the average molecular motion of the remaining water is lowered and thus the temperature is also lowered. And this is the reason we say that the evaporation it is a cooling process. Now next is condensation. It is the reverse of the evaporation and it occurs when the water vapor changes to the liquid state. And during condensation, the water vapor molecules they release the energy and it is referred as the latent heat of the condensation and it is having the amount equivalent to what was absorbed during the evaporation. So, when the condensation occurs in the atmosphere, it results in the formation of the fogs or the clouds. We saw these four processes when solid is converted to liquid and liquid is converted to the gases. But there are two more processes when solid is directly converted into gases or gases is directly converted into the solid state. So here we have one process, sublimation. So the sublimation, it is the conversion of a solid directly to the gas without passing through the liquid state. And the example of sublimation is the gradual shrinkage of unused ice cubes in the freezer. Because these solids are directly converted into the water vapor, which is removed by the dehumidifier in the refrigerator. Another process is the deposition, which is the reverse of the sublimation, means the water vapor is directly converted to the solid state. And we can see the deposition as ice on the solid objects such as the grasses or the Windows pen. And these deposits are called white frost or simply frost. Now, coming to our main topic, humidity, that is the water vapor in the air. So, humidity is the general term which is used to describe the amount of water vapor in the air. So, here we have the water in the liquid state, and this symbol is representing the water molecules. And in the atmosphere or in the air, these symbols are representing the oxygen and the nitrogen. And here we can see some of the water molecules also. So the water vapor, it constitutes only a small fraction of the atmosphere, and it can range from 0.1% to about 4% by volume. And this water vapor is the primary source of energy in the form of the latent heat for the formation of the weather systems like the thunderstorms, tornadoes, and the hurricanes. Meteorologists, they use absolute humidity, mixing ratio, vapor pressure, relative humidity, and the dew point to express the water vapor content of the air. So these are the methods or ways by which the humidity in the atmosphere can be expressed. So we will learn about each of them in detail. Absolute humidity, this is represented as the mass of water vapor in a given volume of air. So here we have the formula, absolute humidity is equal to mass of water vapor in grams divided by volume of air in the cubic meter. But as the air moves from one place to another, changes in the pressure and the temperature, it may cause the changes in its volume. So, when the volume changes, the absolute humidity also changes, even if the mass of water vapor is constant. So, it is difficult to monitor the water vapor content of a moving mass of air when we are using the absolute humidity. Therefore, the meteorologists, they generally prefer to use the mixing ratio to express the water vapor content of the air. So the difference is, here we have in the denominator part mass of the dry air in the kilograms. So the mixing ratio is the mass of water vapor in a unit of air compared to the remaining mass of the dry air. And इसका formula है mixing ratio is equal to mass of water vapor in grams divided by mass of the dry air in kilograms. So suppose if we are considering 1 kg as the unit of air, so in that 1 kg, what is the mass of water vapor? That will be written here, and the remaining mass means the mass of the dry air, that is written here. So when we calculate this, we will be getting the mixing ratio. And as it is measured in a unit of mass, means usually grams per kilograms, the mixing ratio is not affected by the changes in the pressure or the temperature. It would be more clear from this image. Here we have one air parcel, and the size of this parcel is 1 meter cube, and the mass of the dry air is 1 kg, and mass of water vapor is 20 gram. Now if we calculate the absolute humidity, that is the mass of water vapor divided by the volume of air parcel. So we have 20 divided by 1, 20 gram per meter cube, and the mixing ratio is mass of water vapor divided by the mass of the dry air. So here we have 20 divided by 1, 20 gram per kg. But as the air parcel rises, it expands. And as it expands, we can see the size of parcel. Now it is 2 meter cube. And the mass of the dry air, it is same 1 kg. and the mass of water vapor is also same 20 gram. But now if we calculate the absolute humidity, that is mass per unit volume, so 20 divided by 2, now it is 10 gram per meter cube. But the mixing ratio is same because it is mass of water vapor divided by mass of the dry air, so it is same. So if we are representing the humidity as the absolute humidity, that will change depending upon the temperature and the pressure, but the mixing ratio it remains unchanged. So mixing ratio is a better representation of the humidity in comparison to the absolute humidity. Another method of expressing the humidity is vapor pressure and the saturation vapor pressure. So the moisture content of the air it can also be determined from the pressure which is exerted by the water vapor. So when there is addition of water vapor into the air, it can be detected by the small increase in the pressure, and this increase in the pressure it is result of the motion of the water vapor molecules that were added to the air through the evaporation process. So this pressure, which is mainly because of the motion of the water vapor molecules, it is referred as the vapor pressure and is defined as that part of the total atmospheric pressure which is attributable to its water vapor content. यानी टोटल एटमॉस्फेरिक प्रेशर का वो पार्ट जो वाटर वेपर की वजह से होता है उसको हम कहते हैं वेपर प्रेशर. Here we have the explanation of the vapor pressure and the saturation vapor pressure through this experiment. It is a closed container which contains the liquid water, and in the upper part we have the dry air, and with it we have the attached pressure gauge which is showing here zero reading. So when the atmosphere is dry, initially more evaporation will occur in comparison to the condensation. So rate of evaporation will be high in comparison to the rate of condensation. And as more and more water vapor are getting accumulated in this particular space, we can see the gauze it is showing the rise in the vapor pressure. So this rise in the vapor pressure it forces more and more water molecules to return to the liquid, and eventually our balance is reached when the rate of evaporation is equal to the rate of condensation, means the number of water molecule returning to the surface is equal to the number of molecules leaving the surface. So at this point the air is said to have reached an equilibrium called saturation. So we can see here it is written saturated air. So when the air is saturated, the pressure exerted by the motion of the water vapor molecules it is referred as the saturation vapor pressure. Now, when the temperature is increased from 20 degrees Celsius to 30 degrees Celsius, with this further increase in temperature, the added energy it increases the rate of evaporation, which means more molecules will leave the surface and will become part of the air, resulting in further increase in the vapor pressure of the air. And this will continue till a new equilibrium is reached between the rate of evaporation and rate of condensation. Thus, we can say that the saturation vapor pressure it is temperature dependent, and at higher temperature it takes more water vapor to saturate the air, and the atmosphere it behaves in the same manner as our closed container, but instead of this lid we have the gravity of the earth which prevents the water vapor from escaping into the space. Here we have the amount of water vapor required to saturate 1 kilogram of dry air at various temperature in the graphical form and tabular form also. So here we can see on the x-axis we have the temperature, and on the y-axis here we have the water vapor grams per kilogram, that is the mixing ratio, and this blue line is representing the saturation mixing ratio, and this is actually the plot of this data. Here we can see minus 40 pe we have the saturation mixing ratio 0.1, 0 pe 3.5, 5 pe 5, 15 pe 10. So when we plot this data, we will be getting this particular graph, and we can see that saturation mixing ratio it increases with increase in the temperature, and for every 10 degree Celsius increase in temperature, the amount of water vapor needed for saturation it almost doubles. So we can see at 0 we are having 3.5, while at 10 degrees Celsius it is 7, which is just double. Likewise, if we see for 5, it is 5. And when we see 10 degrees Celsius increase 15, so यहाँ पे we have the saturation mixing ratio 10, which means at 5 degrees Celsius, if 1 kg of dry air is having 5 gram of water vapor, it is saturated, while at 15 degrees Celsius, the same amount of dry air needs 10 gram of water vapor to be saturated. Apart from temperature, vapor pressure is the other major factor which determines whether evaporation or condensation is the dominant process. When the air is dry, means it is having the low vapor pressure, the evaporation rate is faster. But as the vapor pressure increases, the condensation process also starts, and at the saturation vapor pressure, rate of evaporation is equal to rate of condensation. Another mode of expression is the relative humidity. Relative humidity is the ratio of the air's actual water vapor content compared with the amount of water vapor required for the saturation at that temperature and pressure. So here we have the formula. Relative humidity is equal to mixing ratio divided by saturation mixing ratio into 100. So mixing ratio is the actual water vapor in the air, and the saturation mixing ratio is the maximum water vapor the air can hold at that particular temperature. Relative humidity can also be written as vapor pressure divided by saturated vapor pressure into 100. So the relative humidity is the measure of कि जो air है वो saturation के कितने close है, means how near the air is to saturation ratio. It does not give the actual quantity of water vapor in the air, but based on this, what is the state of air, means how close it is towards the saturation, it is defined by the relative humidity. And as this relative humidity is based on the air's water vapor content as well as the amount of moisture required for saturation, it can change in one of two ways. First, relative humidity it changes when the water vapor is added to or is removed from the atmosphere. Second, because the amount of moisture required for saturation, it is the function of air temperature, relative humidity also varies with the temperature. So increasing moisture or decreasing temperature both result in an increase in the relative humidity. Here we have the explanation of how the relative humidity changes with addition of water vapor in the atmosphere. In all the three cases, we have the same temperature. And from this table, we can see the saturation mixing ratio at 25 degrees Celsius is 20 gram per kg. So here it is mentioned that saturation mixing ratio at 25 degrees Celsius is 20 grams and the water vapor content is 5 gram. As here we have 1 kg dry air plus 5 gram water vapor. So mixing ratio, that is the mass of water vapor divided by mass of dry air, it will be 5 gram per kg. So the relative humidity that can be calculated by mixing ratio divided by saturation mixing ratio. So here it is mentioned 5 divided by 20. So it is 25%. Now in the second case, saturation mixing ratio, it remains the same, but the water vapor, it is 10 gram. Now the mixing ratio here we have 10 divided by 1, 10 gram per kg. So relative humidity, it is the ratio of mixing ratio divided by saturation mixing ratio. So 10 gram per kg divided by 20 gram per kg. So here we have the value 50%. Similarly, in the third case, the water vapor content is increased to 20 grams. Now, here we have the mixing ratio 20 gram per kg. And if we calculate the relative humidity, we can see it is 100%. So here we can see with addition of the water vapor in this particular flask, the mixing ratio is actually increasing, and thus we can see the relative humidity is also increasing. Here we have the effect of temperature on the relative humidity. Now, in this case, the temperature is 25 degrees Celsius and the water vapor content is 10 gram. So, mixing ratio will be again 10 gram per kg. but the saturation mixing ratio at 25 degrees Celsius is 20 gram per kg. So when we calculate the relative humidity by dividing mixing ratio by saturation mixing ratio, so 10 divided by 20, it is 50%. Now when the temperature is decreased from 25 degrees Celsius to 15 degrees Celsius, here we have the same water vapor content, 10 grams, but the saturation mixing ratio at 15 degrees Celsius is 10. Now here in this case, the mixing ratio, if we calculate 10 gram divided by 1 kg of dry air, so we will be having the 10 gram per kg. So when we calculate the relative humidity, it will come 100%. Now as the temperature is further decreased, it is cooled to 5 degrees Celsius, we can see some of the water vapor is condensed to liquid. So now this flask is having the 5 gram of water vapor and 5 gram of the liquid water. So in this case, if we calculate the mixing ratio by dividing the mass of water vapor from mass of dry air, so we have the value 5 gram per kg. But the saturation mixing ratio at 5 degrees Celsius is 5 gram per kg. So again, when we calculate relative humidity by dividing mixing ratio by saturation mixing ratio, so 5 gram per kg from here and 5 gram per kg from this particular table, so again we are having the 100% humidity. So here we saw as we decrease the temperature, relative humidity increases. But if we further increase the temperature, it will result in the decrease in the relative humidity. इसके लिए you can consider a scenario if we increase the temperature from 25 degrees Celsius to 40 degrees Celsius and we are having the same water vapor content 10 gram. तो उस केस में we'll be having the mixing ratio 10 gram per kg, but the saturation mixing ratio at 40 degrees Celsius is 47. So when we calculate the relative humidity, we will be having 10 divided by 47. So calculate how much is it coming. It will come approximately 21.27% something. So with increase in temperature, relative humidity decreases, and with decrease in temperature, relative humidity increases. There is difference between relative humidity and absolute humidity. Absolute humidity also depends on temperature, but it changes only if the volume is affected by the change in temperature. But relative humidity, it decreases or increases with fluctuation in temperature. As we saw, this relative humidity is based on two parameters, mixing ratio and saturation mixing ratio. So mixing ratio, it depends on the water vapor in the air, and this is independent of temperature. But the saturation mixing ratio, it defines the water vapor capacity of the air or atmosphere, and it depends on the temperature. So in this image, with the help of the bar diagram, it is explained that how relative humidity changes with increase or decrease in temperature. The length of this light blue color is representing the water vapor capacity of the atmosphere at different temperature, and this dark blue color is representing the absolute amount of water vapor, and we can see in all the three cases this amount it is same. Here, of this water vapor capacity, only half is filled with the water vapor, so here we are having the 50% relative humidity. With increase in temperature, we saw that the saturation mixing ratio it increases, so the warmer air they have the greater capacity, and as this part is unchanged but this has increased, so the relative humidity it decreases. But at the colder temperature, the saturation mixing ratio it decreases. Thus we can see here also the capacity is less in comparison to the normal condition. So here we have higher mixing ratio, less saturation mixing ratio, thus relative humidity increases. This explains the reason of high value of relative humidity in the cold winter day and less value of relative humidity in the warm summer day. At colder temperature, though it is having the high relative humidity, but it is having the low water vapor content, and this explains why many Arctic areas they receive very less amount of precipitation, and why we frequently experience the dry skin and the chapped lips during the winter month, because at colder temperature the atmosphere contain less amount of the water vapors. Relative humidity is also affected by the daily changes in temperature, means daylight versus nighttime temperature. So here we can see this red line is representing the temperature fluctuation in 24 hours. This we discussed in our last video. So maximum temperature is around at 4 p.m. and the lowest temperature is around 6 a.m. So we can see the humidity graph is just opposite of it. When we are having the lowest temperature, we are having the highest relative humidity, while when we are having the highest temperature, we are having the lowest relative humidity. In this example, the actual water vapor content, that is the mixing ratio of the air, remains unchanged, only the relative humidity varies, and this is mainly because of the change in saturation mixing ratio with the temperature. Another mode of expression of humidity is the specific humidity. It is the ratio of the mass of water vapor to the total mass of the moist air in the sample, and it is also expressed as the gram of water vapor per kilogram of air. But it is different from the mixing ratio, because if you remember, mixing ratio was the mass of water vapor to the mass of the dry air. But ye specific humidity, this is the ratio of mass of water vapor to the total mass of the moist air. And unlike absolute or relative humidity, this specific humidity expression, it remains constant even when the temperature and pressure changes, as long as no moisture is added to or is removed from the air. Next is dew point temperature, which is also referred as the dew point. It is the temperature at which water vapor begins to condense. This term dew point, it comes from the fact that during the nighttime hours, objects which are near the ground, they often cool below the dew point temperature and they become coated with the dew. So, near the Earth's surface, when the air is cooled below its dew point temperature, it generates dew or fog if the dew point is above freezing. But if the dew point temperature is below freezing, means 0 degree Celsius or 32 degree Fahrenheit, then in that case, frost occur, means deposition of the ice on the objects. Dew point can also be defined as the temperature at which air reaches the saturation, and hence it is directly related to the actual moisture content of a parcel of air. As we saw earlier, that the saturation vapor pressure is temperature dependent, and that for every 10 degrees Celsius increase in temperature, the amount of water vapor needed for saturation doubles. As this dew point is the temperature at which saturation occurs, high dew point temperature, it equate to moist air, and low dew point temperature, it indicate the dry air. Thus, this dew point is an absolute measure of the moisture content in the air, and it is independent of the current air temperature. When it is having the low dew point, it means the atmosphere is having the less water vapor content, and when we have the perspiration, जो भी sweat हो रहा है, that will evaporate easily because there is room in the air for more water vapor molecule. And when it is high dew point, it means the air or the atmosphere is already having the more water vapor. And जब हमको perspiration हो रहा है, जो भी sweating हो रही है, the sweat it builds up and it won't evaporate क्योंकि air is already full of water vapor molecules. And this lead to the feeling of discomfort in the hot weather, as sweating is less effective in cooling the body. So, as this dew point, it marks the temperature at which water vapor will turn into the liquid water droplets. The higher the dew point rises, the greater is the amount of moisture in the air. So, here we have the dew point scale versus how it feels. And if you want to know just how dry or humid it will feel outside, look at the dew point instead of the relative humidity. The higher the dew point, the muggier it will feel. So here it is mentioned the dew point in Fahrenheit. When it is in range 45 to 50, it is extremely comfortable. And we can see as the dew point is increasing, the comfort level is decreasing. So here we have the dew point in Fahrenheit also, dew point in Celsius also, and the third column is how it feels. So dew point when it is less than 0 degrees Celsius, comfort it varies. At lower value, the air could be too dry for some people. 0 to 9, it will still be comfortable, but with the drier air, 10 to 12 degrees Celsius dew point, it is very comfortable. We can see till 15 it is comfortable, but the value of the dew point above 16 degrees Celsius, they are representing the humid conditions. And the discomfort level, it increases with increase in the dew point. Now coming to the measurement of the humidity. So the moisture content of the air or the humidity is measured using an instrument known as hygrometers. And as it is difficult to directly measure the absolute humidity and the mixing ratio, most of the hygrometers they measure either relative humidity or the dew point temperature. अगर हमको इन दोनों में से कोई एक पता है और हमारे पास टेम्परेचर का डेटा है, we can easily convert to any of the other humidity measurements. Most commonly used hygrometer is psychrometer. A psychrometer, it consists of two identical thermometers which are mounted side by side. And if this psychrometer is connected to a handle, it is referred as the sling psychrometer. So, in both the cases, one thermometer it is referred as the dry bulb thermometer, which measures the air temperature, and the other is referred as the wet bulb, and it has a thin cloth wick tied at the bottom. This wick is saturated with water, and a continuous current of air is passed over the wick, either by swinging the psychrometer if it is a sling psychrometer, or by using an electric fan to move the air past the instrument. In sling psychrometer, these thermometers are swung like this around the handle, and in this process water it evaporates from the wick, which cools the wet bulb thermometer, and the amount of cooling that takes place is directly proportional to the dryness of air, because if the air is already saturated, no evaporation will occur, and both these thermometer will have the identical reading. But if the air is dry, means if it is having the less water vapor, more evaporation will occur and greater will be the cooling. Therefore, the larger is the difference between the wet and the dry bulb temperature, the lower is the relative humidity. So, using the psychrometer, we get two readings, dry bulb temperature and wet bulb temperature. Dry bulb temperature is the temperature of the air measured by the regular thermometer without considering the moisture, while the wet bulb temperature is the lowest temperature to which air can be cooled by the evaporation of water into the air at a constant pressure. And this wet bulb temperature will always be less than or equal to the dry bulb temperature, and this indicates how much the air can be cooled down through the process of evaporation. Another parameter is the wet bulb depression, that is the difference between the dry bulb temperature and the wet bulb temperature. Once we have these two data, we can use the psychrometric chart to calculate the relative humidity. A psychrometric chart is a graph that displays the physical and the thermal properties of the moist air at a constant pressure, such as the dry bulb temperature, humidity ratio, relative humidity, and the enthalpy. Here is a psychrometric chart taken from the Wikipedia, and we can see different parameters on this graph. These green vertical lines they are representing the dry bulb temperature. यहाँ पे these purple horizontal lines they are representing the humidity ratio gram water per gram of dry air, and these oblique light green lines they are representing the specific volume. अब यहाँ पे if you see this light blue color, it is representing the wet bulb or the saturation temperature, and you can see these oblique lines. And these black lines are representing the enthalpy at the saturation. And these red lines are representing the percentage relative humidity. Now we read about the wet bulb saturation temperature, dry bulb temperature, humidity ratio, and the relative humidity. There are two new terms, enthalpy and the specific volume. So the enthalpy, it refers to the sum of the internal energy of the moist air, and it includes the heat of the air as well as the heat of the water vapor in that particular air parcel. Another term is the specific volume. It refers to the total volume of the moist air mixture that contains exactly 1 kg of the dry air. Now, this moist air mixture, when we are saying, it is actually the mixture of the dry air plus water vapor. Now let us see how this dry bulb temperature and wet bulb temperature can be used to calculate the relative humidity using the psychrometric chart. Here we have these two readings. Dry bulb temperature is 85 degree Fahrenheit and the wet bulb temperature is 65 degree Fahrenheit, and the wet bulb depression is 85 minus 65, 20 degree Fahrenheit. So on this psychrometric chart, here we have the dry bulb temperature. So let us see, this is 85 degree Fahrenheit. And here we have the wet bulb temperature, that is 65 degree Fahrenheit. So on this particular point, here we have the relative humidity 33%. In the second scenario, when we have the dry bulb temperature as well as wet bulb temperature both as the 85 degree Fahrenheit, we can see here this is the dry bulb temperature and this is the wet bulb temperature. So at this point, the relative humidity is 100%. So as we saw, if the difference between the wet bulb and the dry bulb temperature is less, the relative humidity will be more. Another type of hygrometer is hair hygrometer, and it is one of the oldest instrument to measure the relative humidity, and it operates on the principle that hair changes length in proportion to changes in relative humidity. Hair lengthens as the relative humidity increases and they shrink as the relative humidity drop. So a hair hygrometer, it uses a bundle of hairs linked mechanically to an indicator that is calibrated between 0 to 100%. Nowadays, we are having the more advanced technologies which comes under electric hygrometers. A variety of electric hygrometers are widely used to measure the humidity. There are various types, and here we have the two example. One type of electric hygrometer, it uses a chilled mirror and a mechanism that detects the temperature at which the condensation begins to form on the mirror. So it actually measures the dew point temperature. Another type of electric hygrometer, it works on the principle of capacitance, a material's ability to store an electric charge. This sensor, it consists of a thin hygroscopic film which is connected to an electric current. And as this film absorbs or releases the water, the capacitance of the sensor changes at a rate which is proportional to the relative humidity of the surrounding air. Thus, the relative humidity can be measured by monitoring the changes in the film's capacitance. These are the two examples within the electric hygrometer, but there are various other which work on different principles. Some of them uses the higher technologies like the uses of thermistors. In last video, we saw the definition of the heat index, which is an index for the human discomfort. This heat index is also known as the apparent temperature, and it is actually the temperature how we feel or what it feels like to us when the relative humidity is combined with the air temperature. When the body gets too hot, it begins to perspire or sweat to cool itself off. Now, depending upon the humidity of the air, the perspiration may evaporate or may not. If perspiration is evaporated off the body, it effectively reduces the body's temperature. But if it is not evaporated, the body cannot regulate its temperature. So this evaporation of the sweat from our body, it depends on the relative humidity or the actual moisture content. So when the atmospheric moisture content is high, the rate of evaporation from the body, it decreases. But when the relative humidity decreases or when the atmospheric moisture content is less, the rate of evaporation, it increases. So here we have the heat index prepared by the National Oceanic and the Atmospheric Administration. On the y-axis we have the relative humidity, and on the x-axis here we have the temperature in degree Fahrenheit, and we can see there are the index value and different color coding. We can see the red one is showing extreme danger and the yellow one is representing caution. So depending upon the value of the relative humidity and the temperature in the atmosphere, we can see the index value for the atmosphere, and accordingly here we have the classification, heat index and effect on the body. So here we have the caution, danger and extreme danger, and accordingly we can see different effects on the body. These are the references for this video. Majority of the content have been taken from this book, The Atmosphere and Introduction to Meteorology. There is a chapter, Moisture and Atmospheric Stability. So this video is the explanation of that particular chapter. Some of the content have been taken from these two sites. We will meet soon in the next video. Thank you and best wishes.